So I'd like to thank you all for coming out again. I promised yesterday this talk is disjoint from yesterday's one, and I'll keep that promise. I think the main thing they have in common is that they're both about groups. I mean, yesterday the group was PSL2Z, and today it's going to be a different group, and the main open problem for this group is very closed for PSL2Z. Anyway, I'd like to also thank Dave Pennies for setting me up with a round of golf this morning. That was very, very nice. You got a very pleasant golf course there, and I'd like to thank him also for being the really complete host by letting me find almost all of his balls in the course of the round. I told him I was charging $10 a ball, so he's a fairly major debt to all right, anyway, so I want to talk about some unitary representation of R. Thompson's group. So you notice it's R. Thompson, and the first thing is that there's another Thompson who's famous for groups, and that's John Thompson. It's not him. So the question is, who is Richard Thompson? Anyone here know? Put their hands up. No. It's a sort of a bit of a mystery. He was a Berkeley person, and during my 28 years at Berkeley, I never saw him at Berkeley. He was a student of Ralph Mackenzie's, and Ralph had gone to Vanderbilt. You see, I sort of followed in Ralph's footsteps going from Berkeley to Vanderbilt, but Thompson stayed in Berkeley, and he was I didn't find out about him until a few years ago, till I did some research to get to the bottom of who he was for my talks on the Thompson group. You won't find too much about him on the internet, but he apparently was somewhat autistic, and for many years he's been working on helping autistic kids do mathematics. So he did his work on the Thompson group, which was very, very nice. It came out of logic considerations. Today it won't have anything whatsoever to do with logic, at least not that I know. All right, so he's still around Berkeley, and I believe during those 28 years he did come to the occasional seminar, but I was never involved. So all right, so what is this famous? It is famous these days. Very lot of people think about it for all the wrong reasons, in my opinion. But here, let me tell you what it is. So it is the group of all homeomorphisms. So notice homeomorphisms, continuous maps of the unit interval, which fix the endpoints, so that makes them orientation preserving, and they have the following three properties. First of all, G is piecewise linear. Okay, so on the linear maps on some partition of the unit interval into subintervals. Second, it's smooth, which means dead linear, except at a finite number of points, and all of those points are dyadic rationals. By the way, just in case someone doesn't know what a dyadic rational is, it's a number of the form a over 2 to the b, where a and b are integers. Now you wonder why, if a are integers, you write the 2 to the b in the denominator. Well, psychologically, right? It's a over 2b. As b gets big, it's got to be a little number. All right. So now the slope, dgdx of G as the map, when it's defined, is an integral power of 2. So the points at which it breaks and becomes discontinuous are dyadic, something over 2 to the n, and then in between them there's always a slope which is 2 or half or 4 or 16 or something like that. Okay, so that's the definition of the Thompson group. It's the set of all of those. It's the set of all of those homeomorphisms having that property. Okay, there's another one. I think in the title I probably mentioned Thompson's group T, maybe I didn't. Thompson's group T is just the same as F, except instead of having it on the unit interval, you have it on the circle. Okay, so you add to the Thompson's group as defined, you add rotations by dyadic rationals, and look at the group that generates, and that's the Thompson group T. Okay, so two groups of homeomorphisms, one homeomorphism of the interval, second homeomorphism of the circle, And the circle ones are allowed to rotate as well. Okay, so if you have one on the T, then you can just rotate it back so that it fixes the point, whatever it is, and then it becomes an element of F. So T is somewhat bigger than F, but similar in spirit. Okay. All right. So next up, Cannon-Floyd-Parry. Yeah, if you want to read about this, there's a truly excellent piece of article that you'll find by googling immediately. If you just Google Cannon-Floyd-Parry, you'll get about 20 hits to the notes that Cannon, Floyd, and Parry wrote about Thompson's group, and I recommend them as a model of mathematical exposition. Okay, they rival Serre, I think, in their elegance and clarity. So, right now, question is, how can we draw a picture of an element of Thompson's group F? Well, the most obvious way is by its graph. Okay, so here's the graph. So here's an element which, I'll tell you about it, you'll all agree that it is an element of Thompson's group. In between 0 and a quarter, it has a slope of 2. So it goes up to a half there. In between a quarter and a half, it has a slope of 1. So it goes from a half to 3/4. And then in between a half and 1, it has a slope of a half. So it ends up being back at 1. So there it is. It's a homeomorphism because there's no gaps. And satisfies all the breakpoints are a quarter, a half, and 1. And the slopes are all powers of 2. So this is one of the standard generators of the Thompson group, which is called A. Whoops. This element is called A, right? Very imaginative, letter chosen for this is A. All right, the next imaginative letter is B, and this is B. Okay, so B is like A, except that B happens in between a half and 1. Right, so in between 0 and a half, for B, we just have a slope of 1, and then you just take A and then compress it down to that half interval. So it goes up and flat and then back down. Right, so that's B. So we have A and B. So now we know what they are. All right, so that's, right. So as I said, you can draw a graph, but you can see already that that's a little bit limited in clarity, right? You just get this wiggly line. All wiggly lines are sort of equivalent after you look at them for a while. So we want some better ways of drawing elements of the Thompson group. Here's one, which I kind of like, where you put the domain is at the bottom. It's this unit interval here. The range is here. And these intervals, this interval 1/4 gets expanded up to 0 1/2. The interval between a quarter and a half just gets shifted along to a half and 3/4. And the interval from a half and 1 gets scrunched down a bit to 3/4 1. Okay, everyone clear on that? And if you like, you could fill this in with a sort of foliation, piecewise linear foliation, where you just join a point on the bottom to its image on the top. Okay, so that's a nice way. Now that I hope you agree, that gives you a somewhat better conceptual idea of what's going on than just the squiggly line. All right, so B, now it's clear what you do for B. B is just nothing happens between 0 and a half, everything goes straight up. And then you just take the picture of A, squish it down and put it next to it, and that gives you B, right? So A and B are the standard elements of the Thompson group. And it turns out that they actually generate the Thompson group. So that's rather nice. You just have these two rather simple elements that are sort of the same thing. There's no new phenomenon going from A to B. But together they do generate the Thompson group. And if you want to see a nice argument for that, Cannon-Floyd-Parry, beautifully done there. All right, so moving on. Yeah, there is a clock. Properties of F. First of all, F is a group. Not very hard, right? Slopes, compose, multiply, blah, blah, blah. Okay, F is a group. Any other questions about that? Well, it's a group, and what question does someone want to ask me straight away? It's a group. What is it? Is it No. That's cheating. That is cheating. Out. Yeah. Is it finite? No, it's not finite. In fact, it's torsion-free, because if you just start composing any of these elements, you can never, as soon as something is scrunching like that and so on, it's pretty easy to see that it's not finite. T actually has some torsion in it, but F is torsion free. All right, any other questions? We have a group, is it? All right, is it simple, right? That's clear. Okay, so is it simple? Is it simple? No, it's not simple. And the reason it's very simple, right, it is that if you look near 0, then there's this, it's always got to be a straight line, and that has a certain slope. And that slope is a homomorphism. If you take its log, it's a homomorphism to all powers of 2. Right? Because we said that the slope, and similarly at the other endpoint, that's slope of power of 2. So there's two essentially independent homomorphisms from the F to Z. I just said the one at 0, but there's also one at, right, I didn't, in the notes, I just told you more than is written here. There's another one, there's one to each end, right? So it's two homomorphisms from Z plus Z, and it turns out that F, the commutator subgroup, is actually the kernel. So this is the universal abelian quotient, this is Z plus Z. If you want a nice proof of that, Cannon-Floyd parry, right? All right? And the commutator subgroup itself, that is a simple group. So it's an infinite simple group. And back in the day when Thompson was discovering this, there was interesting questions. If you got a countable, discrete, simple group, then you know that was an interesting thing. They weren't too thick on the ground then. Right. So is it finitely presented? Next question. Well, yes, it is. And not only that, but as I said, it's presented on these two generators, A and B, and two relations, which are, you know, magnificently, intuitively clear from these formulae. No, they're not, right? But what both of those formulae express is that if you write down these elements of the Thompson group, then they are disjoint. They're supported in disjoint intervals, so therefore they necessarily commute. So these are two relations that say one thing commutes with another, and what they correspond to is this natural geometric notion of two things commuting if they're in disjoint supports. So it turns out that that's enough. And if you want a proof of that, elegant proof, Cannon-Floyd parry. Right. So here's an interesting thing. There's no free subgroups. So unlike PSL2Z, which we were dealing with yesterday, which has a free subgroup of finite index, there's no free subgroups at all of this Thompson group. And that you sort of get the feeling for that if you start playing with, you know, there's a lot of commutativity going on by scaling things down, and then you can get things happening in these little intervals. And in fact, every non-commutative subgroup contains Z squared. Okay, and in fact it contains a free group of infinite rank once it contains Z squared. Okay, so now that probably leads to the question, oh, T, right. T on the other hand actually does have free subgroups. You can get a Z mod 2 coming from the rotations. You can get a Z mod 2 and a Z mod 3, and they generate a free product of Z mod 2 and Z mod 3. So there's definitely PSL2Z is sitting in there, and therefore there's free subgroups. All right, now we have the question that was, is F amenable? Okay, so this is the big question. For some reason, it's not known whether F is amenable or not. So what's amenable? Amenable is a property invented by von Neumann. And well, the easiest way to say it is that there's an invariant finitely additive measure on the set. So there's a finitely additive measure on the set, which is invariant under translations. Okay? That's a horrible way, it's a very easy to say, but it's a horrible thing to think about, because the only way that you can actually explicitly exhibit, well, you can't explicitly exhibit them, you've got to get them as limits, you know, ultrafilters or, you know, some kind of things that you can't quite get your hands on. Right? But there are, yes?
I'm wondering, in your presentation in
Yeah.
part 3 of the group, you have AA, you also have A squared and A squared A.
Yeah, I think the reason for that is I've tried to exhibit these things as commutation relations. This relation says A, B inverse, A inverse commutes with BA or something. Well, it should say that. Or so, AB inverse commutes with A inverse BA, right. That's why I put this. If you draw those pictures, you'll see what I mean about they commute because they're in different disjoint supports. Now, where was it? Oh, amenable, right. So a much better way to say amenable is that for every epsilon, there's a subset which is up to epsilon, measured in the right way, invariant under translation. So the integers, for instance, are amenable because if you take a large interval in the integers like that and shift it by 1, you've done almost nothing. Okay? And these sets that are almost invariant are called Fellner sets. And the question is, does F have Fellner sets? Okay. Well, it's known that if a group has a free subgroup, then it's not amenable because you can do these funny games with free groups and push off and this ping pong, so-called ping pong. But so T, the other Thompson group, is certainly not amenable. But F, it's an open question. And at least a few years ago, it was true that every so often there would be a proof sort of published or on the archive of amenability or non-amenability, and they would sort of alternate, and Sapir would shoot them down every time they appeared. But there hasn't, I don't think there's been a new one since for a few years since I got into the game. So it's still an open question. I'm not. Oh, sorry, I shouldn't say that. I'm not in the game of trying to prove that it's amenable. That, for me, that's an interesting question. But I gave up on it as soon as I started because there's some really neat work that's been done. This guy Moore, someone Moore, I've forgotten his first name. Sorry, the expert here can tell me. Anyway, there's a question of how. As epsilon gets smaller and smaller, how fast do these Fellner sets have to grow? And Moore showed that Justin Moore, is it? Yeah. He showed that they have to grow sort of not just but sort of logically fast as a function of epsilon. Ackermann function fast as a function of epsilon. Yeah, he was one of the wrong proofs, but he redeemed himself thoroughly by turning into a proof of this very interesting thing. So that means that checking it by computer is sort of impossible, or it's going to be extremely difficult. And that was evidenced by the strongest person that I know, that kind of thing, got into the game name of Hagerup. And he, together with his son and someone else, got a computer, and all the tricks that Hagerup could throw at it. The actual there's a criterion for, sorry, I'm going to use up all my time before I even get started here. There's a criterion for being amenable for a group with two generators, and that is, well, let me say it this way. There's a group has a Cayley graph where you have the group elements and then you go from one to the other according to whether there's a generator that connects them. And you can try and count the loops on the Cayley graph. Count the loops on the Cayley graph. And then the idea is that as the length of the loop gets longer, group is amenable if and only if the sort of exponential growth of that is 4 to the n. So you take the log and you get something that should tend to 4. You get this function of the length which should tend to 4. And by these cunning Hagerupian tricks, every kind of thing was thrown at it, and every kind of, and the graph sort of so here's 4 and here's the length of the, and it sort of looks like this. And then it choked, right? Even with all of these wonderful tricks and the best computers available. So does that tend to 4 or something less than 4? It tends to something, that's known. But so the evidence was inconclusive. So super, super hard problem, okay? So I thought, well, don't want to try that one. Don't recommend it to any graduate student or anything like that. Plus, there's absolutely no corollaries as far as I know. It's not good for anything, except to become famous. All right. So now I want to get on to the next, the meat of this talk, which starts with another way of describing elements of the Thompson group, which is less obvious, but extremely powerful. Okay, and so I have to have a little aside and talk a little bit about this tree of standard dyadic partitions. So I've got some words which of course come from Cannon-Floyd-Parry. All right, a standard dyadic interval is one of the form a over 2 to the n to a plus 1 over 2 to the n. So that's like, well, it's a cheat, 0 to 1/4. Right? Well, 1/4 to 1/2, there's a good one. It goes from 1 over 2 to the 2 to 2 over 2 to the 2. A quarter to 3/4 is not standard. It's dyadic, but it's not standard. Okay? So a standard dyadic partition is a partition of the interval from 0 to 11. That's a typo. From 0, the interval from 0 to 1. Yeah, left over, right. Right, 11 is what, 23 minus 1 over 2. 23, yeah. Now, a standard dyadic partition, so standard dyadic, the point is that standard dyadic intervals in 0, 1 form a planar binary rooted tree under subdivision. So I'll tell you what. Something has gone wrong. We need. It could be if it's a PDF file. We have to get onto the computer. I think we're on. Okay, so there's something wrong with the PDF file. Did it get transformed? Can you read it from the stick?
I'm just going to try to see if it, yeah, something went in with the PDF file. I don't know
Okay, where's the stick? I'll put it on again. This is the fault of Apple. Because Apple eliminated their USB thing in their latest, so you've got to have this funny dongle and it doesn't work well. Oh, it's there. No. Sorry, my apologies to Apple. It's wonderful software, yeah. Always worked. Yeah, it's good. That's what we want. All right. Thank you. All right. So, where was I? The standard dyadic intervals form a planar binary rooted tree. So here it is. It's the simplest thing imaginable. You just take intervals and split them in half each time. So, you know, this is it. 0, 1 is the top one, that's the root of the tree. And then 0, half, 1, 0, quarter, split this one in 2, and so on. Okay? Nothing to it. All right. And standard dyadic partitions, so a standard dyadic partition is a partition into standard dyadic intervals. Then I claim that you can see them, this is slightly more subtle, as full subtrees of the above tree. So, for instance, the partition 0, quarter, the one that we were dealing with for defining A, is given by the subtree in red. So the red lines form a full subtree. I don't know whether full is standard, I invented that term. It just means that every time you go down, you've got to take both branches in the tree. Oops. So there's a full subtree. And yeah, it's just simple to check that if you have a dyadic partition, then the leaves of this tree, which is 0, quarter, quarter, half, and a half, 1, that's obviously a partition. Every standard dyadic partition happens in that way. That's as trivial as subdividing by 2. Almost as obvious is the first lemma, which is elegantly proved in Cannon-Floyd-Parry, is that for each element of the Thompson group, there is a standard dyadic partition. First of all, such that the breakpoints in the function, the points where it's not smooth, happen at the endpoints of that standard dyadic partition, if they happen. And so that's just saying G is smooth on the interiors. And not only that, but the images under the Thompson group of those intervals are also standard. Okay? So if that doesn't happen, if your Thompson group does something else, then you just keep refining until it happens. It's not very hard. There's the proof. So it follows immediately from this lemma that every element of the Thompson group can be defined by a pair of planar rooted binary trees. Because you see, it suffices to know the I1 up to ik, and then g of I1. So this is another standard dyadic partition, and g sends I1 to g of I1 and I2 to g of I2, right? So if you know the initial partition, the N1, you're done. So, and also it's true that whenever you have a pair like that, then you can define an element of the Thompson group. You just send the intervals on the first partition to the intervals in the second partition, starting from left to right, in the only way possible, because you've got to slope them. They all have width powers of 2. Okay, so that's good. So in fact, a better way, the best way of thinking about elements of the Thompson group is as pairs of planar rooted binary trees. So let's see what happens for our element A. So here's the pair. So this is the first planar binary rooted tree here. Here's its leaves, interval 0 1/4, interval 1/4 1/2, interval 1/2 1, and here's the image ones. So this pair defines the Thompson group element which sends 0 1/4 to 0 1/2, 1/4 1/2 to 1/2 3/4, and 1/2 1 to 3/4 1. That's our element A. Okay? So forget all those intervals, just look at that pair of trees and you've got an element of the Thompson group. That's A. Okay? Now, the representation of an element as a pair of planar binary rooted trees is not unique, but it's almost unique. There's only one thing that goes wrong, and that's this so-called cancelling of carets. The word caret comes from your computer keyboard where there's that thing that's called a caret. So let me tell you what happens here. So what you can do is you can cancel a caret. So you take the domain one and you add a little caret to that. So we've added a caret there to that one. And then you take the range one and you also add a caret to that. So this little caret has got added there and there. So all you've done in terms of intervals is you've taken an interval on which it's nice and smooth and you've split it up into two intervals on which, you know, it just does, you know, you just split it up, split the interval up into two without changing the function at all. So the theorem is, and of course an elegant proof, blah blah blah, in Cannon-Floyd-Parry, that for each G in F there is a unique pair of binary planar trees defining G with no cancelling carets. In general, if you have a math problem where you get to cancel something, then you have some horrible non-uniqueness, you have moves and so on, and you do it in one order, you get something, do it in another order. And not in this case. Just take a pair of trees, cancel any carets that you see, and at the end of the day you end up with the same pair of trees, and that's the element of the Thompson group. Okay, so we can say, if we wanted to divorce ourselves from geometry and topology and intuition, we could say that the Thompson group is the set of all pairs of binary planar rooted trees with no cancelling carets. If you did that, then you would say, well, why is it a group? Okay? Well, the inverse operation is very simple. You just exchange the two, right? And composition, well, I'll deal with that later. We'll come back to that. But before doing that, I want to make things more complicated. Sorry about that. By introducing, instead of just trees, I want to introduce a functorial point of view, which is based on, and things are really going, oh yeah, based on forests. Okay? So we're talking about planar, binary, rooted forests. Okay? So what do I mean by that? Well, what I mean by that is one of these. There's a forest, F. So here's the roots of the forest, the different trees, the roots of the different trees in the forest. And each component of the forest is a planar, binary rooted tree. You can have a bunch of them. Okay, what does the word planar mean? Well, if I didn't say planar, then there'd be some ambiguity about what the ends were. You know, you could just fill it. But once it's planar, then there's only one way to go. Okay, so that's a planar forest. And there's a tree. Oh, I said forest. So now I'm trying to exhibit the fact that forests act on trees. What does that mean? Well, I can take a tree stack a forest on top of it with the right number of roots. The number of leaves of this tree has to be the same as the number of roots of this forest. Stack it on top, and I've got a bigger tree. Right, there it is. So all I've done is that tree, I can think of this tree as being the composition of this tree in this forest. Okay. Also, forest stacked on forests, right? In the same spirit, I can take two forests, and if the number of leaves of this one is the same as the number of roots of this one, I can stack one on the other, and I've got a composition of these two forests. Okay? So obviously, whatever a category is, forests form a category. Planar, binary, rooted forests form a category. The objects of the category as the natural numbers, the number of roots. The morphisms are the planar forest. So this here is a morphism from 3 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 again, okay? So that's the category. So there's a morphism. You can compose two morphisms. You get another morphism, and so on. All right. So that's nice. Some people like categories. Unfortunately. So now we can define an equivalence relation on pairs of planar rooted binary trees with the same number of leaves by the following thing. We say that pairs of trees are equivalent if and only if there exists a forest such that the composition in this category of F with S is the same thing as the composition of F with T. Is that what I mean? In fact, that's exactly what I mean. Right. I thought there might be a typo there. So anyway, that's a perfectly fine definition. But what I want you to recognize there is that is nothing but cancelling carrots. Because every time you add a little twig like that to the tree that you've got, add a carrot to the tree, and then add it to both of them, and then you keep on doing that, and those carrots that you're adding stack up to give you a forest. Okay? So we recognize cancelling carrots. So this equivalence relation, which we've now defined in categorical terms as two trees, which are morphisms from one to something, with the same number of leaves, are equivalent if and only if there exists something in the category that so when you compose it, you get the same thing. This is the same thing as cancelling carrots. Okay? And we have a notation, and this is the key to the whole talk, is this notation. I'm going to write S over T as the equivalence class with this equivalence relation of pairs S and T. Okay, so S over T is an equivalence class of pairs of leaves with the same number of pairs of trees with the same number of leaves up to this equivalence, which is the same as cancelling carrots. So this set of fractions, S over T, is the same as Thompson's group. That's the notation. The notation is S over T is the equivalence class. And if you've ever taught your first, serious math course to undergraduates, that's what you do to do rationals, right? They're sets of ratios, equivalence classes of pairs of integers, where the equivalence relation is actually rather similar to that one. Okay, and how do you multiply fractions? That's the Thompson. How do you multiply fractions? Well, it's simple. R over S times S over T equals R over T. Now, when we're doing that to our undergraduates, they wonder what's going on, because it's such a familiar rule that you don't think of this as being an actual operation on equivalence classes, and it's not immediately defined. It's not quite obvious that you can arrange them so that the denominator of this one is the same as the numerator of that one. But it's so familiar that we just do it. Well, it gets so familiar in Thompson groups that you do it also. So that's the group law. It's not defined immediately when you get a pair of trees. You have to do the stabilization move, and then once you can do that, you can compose them. Okay? So this is a group of fractions. What we see is that the Thompson group is a group of fractions for the category of planar binary forests. Now, there was this guy, Norwegian, whose name if there's any Norwegians in the room, they could pronounce it for me. It's probably OR or something like that. Anyway, I think commonly called OR in English. And he showed that if you have a semigroup, then under certain conditions you can form a group of fractions for that semigroup. And this is exactly the same procedure, and there's a generalization of this that works for lots of other things besides Thompson groups. So that if you have a category, blah, 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 you can form a group of fractions. It's essentially the same idea as OR. Right, now let's have a picture of this. Here is S and T. So this is a pair of planar binary rooted trees with the same number of leaves. I'm going to represent them sort of, what's the word, quirkily. I'm going to turn one of them upside down. I'm going to have S, I guess, what have I got? I've got S on the top and T on the bottom, of course, S over T. But I'm going to turn one of them upside down. I guess I've turned T upside down, and then I'll join the edges. So this picture here represents this element of the Thompson group. And you can immediately think of it in terms of intervals. These guys on the top, that's the interval 0 1/4. On the bottom, it's the interval 0 1/2. And the Thompson group element sends that interval to that interval, sort of at that point. Okay, so there's yet another notation for elements of the Thompson group. Is everyone clear on that now? It's just the same as we've done several times. We've got the tree on the top, tree on the bottom. I've just decided, I still can't, my brain's not giving me the right word, adverb, to flip one of them upside down. Okay. All right, so that's the Thompson group. Pairs of binary planar rooted trees under this equivalence relation given by the action of forests. Planar binary rooted forest. But forests can act on lots of other things, this category. So you can look for more, and to say action in category speak is to say that there's a functor which goes from forest to some other category. Now, the point is that this category of binary planar rooted forests is very simple to define in terms of generators and relations. And the generators, it's sort of, this is sort of, very easy to believe that if you take these things as generators, so this is just adding a caret, then the relations, I guess I never even put it, it's so obvious. The relations are these ones, once again, about things about having disjoint support. If you add a caret here, first here and second there, that's the same thing as adding it first there and second there. And it's easy enough to see that that actually presents this category of planar binary rooted forests. So it becomes a combinatorial algebraic thing. So all you need to do to get one of these functors is to just say what do the FIs go to and check that those things also have this property, and you've got a functor. Okay? So this, a category theorist would be horrified with me saying this, but what I say is this involves a context and a way that the fork acts. This is what I'm going to call the fork. So here's an example. The simplest possible example that is maybe convincing comes from functional analysis, and it's this. The category, the image category on which forests, for the morphism, is going to be Hilbert spaces. I guess that's something that's in common with yesterday. We had Hilbert spaces yesterday. We've got Hilbert spaces again today. H is some Hilbert space, and the functor phi, this functor, here's an object of the category of planar binary rooted forest. It's just the number of roots. Then that's going to go to the direct sum of n copies of the Hilbert space. Okay. So this is what follows here for a little while is going to be joint work with Arnaud Brottier. This is the context. So it's clear in this context to represent the fork, all we need is an isometry from H to H plus H, nothing else. Because once you're given that, you've got the fork, and it's completely obvious that if you do this thing on the Hilbert spaces, you do one of these things over here and one of them over here, they commute. Okay? So that's it. That's all you need to get a functor. So what is an isometry from H to H plus H? Well, it's just it's a trivial exercise to check that this is a pair of operators, one going A goes from H to the first one, B goes from H to the second one, and they have to satisfy the isometry condition, which is A star A plus B star B is equal to 1. That's it. Okay, so every time you have a pair of operators on Hilbert space with A star A plus B star B equals 1, you have a functor from planar binary rooted forests to Hilbert spaces. So get your minds working on this thing here, A star A plus B star B equals 1. Think about that for a while because I'm going to come back to it. But now let me carry on with the general story. The general story is that every time that you have a functor, or sort of an action of forests, if you like, we get an action of Thompson's group. So this is this sort of new idea. I say that I invented this idea. Possible someone can find it somewhere else, but I haven't seen it, and certainly the examples that have come up seem to be quite new. So it acts on something, and that something is going to be a little bit subtle. That's the point. That's why no one has really had done this before, because you have to work a little bit to show what it acts on. So once again, every time we're given a functor from forest to something, we get an action of Thompson's group, F, and T as well, if we want to. So I'm going to simplify this by assuming that the objects of the category are sets. Every category that I care about, the objects are at least sets. So there's not much of an assumption. If they're not, you can turn it into such a thing anyway. So the trick is going to be to simply mimic the definition of the Thompson group. So if you follow sort of word for word my definition of the Thompson group as pairs of things, equivalence classes, then you'll get this thing just dropping out. So let's go through it. Sorry, this is getting a little bit abstract and you might get a bit lost. But it's only a few lines, and you'll agree at least the formulas on the board are simple enough. All right. So we take, instead of taking the set of pairs of trees, we take the set of pairs where T is a tree with n leaves, and X is something in what an object, something in the set which the functor takes n to. So we have a pair of n trees, we have a tree and something in the image of that functor under that. Okay, and then on that we put an equivalence relation, which is exactly analogous, it's exactly the same really as the one which we did for the cancelling carrots. The pair T of X is the same thing as stabilizing an F with T and stabilizing this with the functor. Phi of F applied to X. If you think about this, X is an element of phi of n, and this is a functor, so this it all passes and you get this makes sense. All right. So this is to be compared with the equivalence relation that we did for Thompson's group. And now we simply, in the same way as we let the Thompson group be the set of all equivalence classes of fractions, we let the something, we use this notation for the equivalence class, T over X. So in the Thompson group, this was another tree. And then the same argument that shows that F is a group, exactly the same, the OR thing, shows that you can define an action of the Thompson group on the set of equivalences classes as S over T times T over X, applied to T over X is S over X, so the T's cancel. Okay, that's kind of sweet. And it all works for exactly the same reasons. So this defines an action of F on the set of equivalence classes for this equivalence relation. And it's just the same as, you know, rationals from integers. In a different language, the set of equivalence classes is known as the direct limit. You can think of the trees as forming a directed set. You can think of the functor as giving a direct direct system, and this is the limit of the direct system. That's just simply exactly writing down what I just said. Okay, so that's what's going on. You have this thing, you have this functor, and then you just build up this big space as the direct limit according to the functor. All right, so now let's come back to this case where C is Hilbert spaces and Y is an isometry. Right, so remember that all you have to do to get an action is tell what the fork does. And the fork was simply an isometry from H to H plus H. So the set on which f acts is a pre-Hilbert space then. You take this direct limit. Everything, since it's an isometry, everything preserves the inner product, so the inner product goes, and the linear structure, all of that goes through to the direct limit, and you find that obviously, tautologically, the action of the Thompson group is by unitaries. Okay? So we've got what I told you I was going to give you. I've got a unitary representation of the Thompson group. There weren't all that many of those known before this construction came along. Moreover, if we're given a vector omega in phi of 1, the very first, so there's the base Hilbert space, and then there's all of these Hilbert spaces going up to the direct limit. You can take a vector right down here and you call it a vacuum, being a physicist. You call it a vacuum, omega, and you call omega this vacuum. So that when you have a unitary representation group, the question you always ask is what are the coefficients? And the coefficients are the matrix coefficients, another way of saying it, or these things here. And once you know these things, they're what's called positive definite functions on the group, you know everything about the linear, the representation, at least as far as omega goes. You know exactly what it looks like. So that's all the information you need. So here's this theorem, which I put in quotes because it's kind of funny, the way I've stated it. This is a joke, right? So you get ready to laugh when punchline. Okay, so if G is S over T, for instance, this pair of trees, then the coefficient of this unitary representation is this. Okay, that's the joke. This is a complex number, right? It's a unitary representation. What's this? Well, the point is that depending on the context, you interpret this picture and you get a complex number. And that's what the theorem is. So I'm going to explain in this context that I just gave of A and B, I'm going to explain how to get from this picture a complex number. And that actually tells you everything you need to know about the representation. So I could say, forget all about the forests and junk and junk and junk. Given this function, prove that it's positive definite, I've got a unitary representation. So, okay, that's the... So the complex number given by this is determined from the pair of trees by the context. The top half is just, well, the bottom half. Well, I don't know what that means, so let's get on. So let's see how it works in an example, in this example plus. All right, so remember plus was you take the direct sum of Hilbert space and you're given this pair A, B, with mappings from the Hilbert space to itself with AA star plus BB star equals 1. So how do you get a number out of that? Well, we have this vector, remember we have this vector omega sitting at the bottom. So what you do is you take the trees, and on the bottom one, you put A's when you go to the left, B's when you go to the right. Okay? And then on the top one, let me skip this a little bit. So, right. Skip the, well, you can forget all that junk. You do exactly the opposite on the top one. When it's going that way, you put an A star, and when it's going that way, you put a B star. Clear? Right? Well, now, if you go from the top to the bottom, you follow a path, right? And as you go up the path, you just simply read those elements. So this path would be A star, A star. Then you could go this one up the middle, it would get B, A, B star, A star, and so on. So for every way of getting from the bottom to the top, you get a word starting with some A's and B's and then their stars. Then the result is that this coefficient is, you take the sum of all of those paths, apply it to the vacuum, and hit it with the vacuum. Right?
What is bottom and what is top?
So the bottom is the one at the bottom, and the top is the one at the top. Did I get it wrong?
No.
No.
You,
A star, A star. B, A, B star, A star. So reading from right to the right is the bottom. And this, that's the bottom starts there. Which one have I got wrong? Second line.
from the top, it's B star and A star. No, low, here.
Because you flipped it.
I flipped it.
You take the adjoint of the picture.
On the top half, the A's go that way, and they become stars. And on the bottom half, they go that way and they're A's. Okay. If you do, I'm pretty sure this is right. I don't think there's any 11s in this picture. So there we go. There it is in words. So even if you didn't follow the construction of all this functor junk, that's it. The theorem is that there is a unitary representation with this as its coefficients. Okay? All right, now to examples, real examples. So it's very instructive to ask a group of mathematicians what examples come to mind when they see this relation. A star A plus B star B equals 1. So let's have a poll. What's the first example that anyone thinks of? Let's say, oh, I didn't mean to do that. So the most obvious one is 0 and 1, right? Yeah, that's not. Actually, that's already non-trivial in this example. If you do 0 and 1, you get an action of the Thompson group on little L2 of the dyadic rationals, basically. But the first one you think of is where you would Pythagoras theorem, cosine and sine, and the simplest one of those is A equals B equals 1 over root 2. Okay, so I said that to that thing there exists a unitary representation of the Thompson group. What is it in this case? Well, you wouldn't guess, I don't think. You wouldn't guess, but I'll tell you what the answer is. The answer is it's the representation on L2 of the unit interval. Okay, the Thompson group acts on the unit interval, doesn't preserve the measure. You've got to do the scaling, another thing we did yesterday, scale by the square root of the Radó-Lectures derivative. Okay, and if you do that, you get a unitary representation, and that's what this choice gives you of A and B, A equals B equals 1 over root 2. Notice that it's continuous, Everything was very discrete before, but this is a continuous representation. All right, I'm going to don't want to run too much out of time, so I'm going to only do one other, I think, and this is a quite amusing one. Another one that you no way you'll ever guess. A star A plus A star. So this is putting A equal to B. Okay. Then A star A plus A star is equal to 1. That's the canonical anti-commutation relations, especially if you put A squared equals 0. Okay, so this is one that physicists know and love. Okay, and you can write this just little 2 by 2 matrices, right? So here the representation turns out to be the following. You take, whenever you have a group and a subgroup, you can always induce a representation from the subgroup up. Right? It's just the action on cosets. All right? So what I claim is that in this example, this is an induced representation, so all you've got to know is what the subgroup is. And the subgroup turns out to be the stabilizer of 1/3. 1/3. This is a bit like the 13, but it's 1/3 for the action on the dyadic rationals. So you look at all Thompson group elements that stabilize 1/3. Notice that that's not a dyadic number. It's a rational, but it's not power of 2 or anything. Look at the stabilizer of that, and you induce up to the whole representation, and that's what you get from fermions. Go figure. Now, it's not, I said I was only going to do 2 examples, but in fact I'm going to do 3, it seems. There's another one. Operator algebraists will always, very quickly after they see that, they'll say Kunz algebra. So there's a thing called the Kunz algebra that comes up, and that Kunz algebra, the rule there is that both A and B are supposed to be isometries. So they you take the Hilbert space, split it up into 2 equal parts, and you define isometries between these parts. Kunz called them S1 and S2, and this corresponds to the map A equals S1 star and B goes to S2 star. And there's a universal algebra with C-star algebra with this as its presentation, and this gives a map to the Kunz algebra from the universal C-star algebra onto the Kunz algebra. Actually, this algebra is quite a bit bigger than the Kunz algebra. But so I just want to say that the following about this: Arnaud and Brottier and I were trying to figure out whether all of these representations actually came from the Kunz algebra. Once you have the Kunz algebra, you represent that on Hilbert space, and that will give you, by composition, a representation of the Thompson group on Hilbert space. And we were trying to figure out whether they all came from that, and we got some pretty neat ways of getting a lot of them. But talking with Anna Marie Bowman, who's at Vandy, she had some category theoretic, homotopy theoretic take on all of this, and she convinced us eventually, or convinced me eventually, that in fact there's a category theory construction which actually makes my reading of it was that in fact, yes, it's true that all of these representations of the Thompson group, which were, you know, like that stabilizer of a third and the L2 of 0, 1, they all actually factor through the Kunz algebra, okay, from this universal action which had already been constructed by Nekrashevich. So it sounded like we'd done all this work in vain, you know, all of this stuff was already known by going via the Kunz algebra. Well, not at all, because in order to show that the representation comes from the Kunz algebra, you have to construct it first. And it's only once you've actually done it using this functor method that you can see that it comes from the Kunz algebra. So in fact, what is actually true is that we're constructing new representations of the Kunz algebra from this thing. So, you know, it's only, you know, we were snap victory from the jaws of defeat. So, okay, if you want, by the way, if you want to see why this algebra is so much bigger than the Kunz algebra, you can just take this. You can take any two unitaries at all, and this pair of A and B will satisfy the relations. So the free group on two generators, the algebra of that, non-amenable, blah, 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 definitely is in this algebra. So the Pythagorean algebra is A star A plus B star B equals 1, surjects onto the algebra of the free group on two generators. All right, I've got to come to the end here fairly soon. So, second example is tensor. So I just do exactly the same as what I did before, except I replace the direct sum by the tensor product. No problem. The fork becomes, instead of being an isometry from H to H plus H, it becomes an isometry from H to H tensor H. And then you interpret the diagram slightly differently. But it's still true that the coefficient is still that diagram, only you read it off differently. And I don't really have time to tell you exactly how to read it off, but let's just say that it becomes, if you choose an orthonormal basis here, then you can represent this in terms of a basis and it has little numbers, coefficients, and you can do some nice statistical mechanical sum. You can think of this as being a lattice model and do the statistical mechanical sum, and that ends up being your coefficient. When I say statistical mechanics and sum, there's something psychologically going wrong here. You're saying, but this is just this tiny little thing. Well, if you have a big element of the Thompson group, it can be a really big pair of trees. And so it makes sense to think of it in terms of statistical mechanics. It's now much more difficult to nail down the Hilbert space. I guess I gave some examples in which that Hilbert space we knew what it was, but in this case it's really a direct limit. Bowman's argument extends to the case where this is a unitary from H to H tends to H, but that's by no means the case in most examples. All right, so now we can extend it from plus and tensor to a tensor category, and you can get these tensor categories from, this is the denouement, this is the end game, right? I saw these guys playing this chess. Now I'm going to play a really rapid game and get to the end of the talk. You can get these, you can replace tensors, Hilbert spaces, by an arbitrary tensor category, and they come from subfactors. And my investigation of Thompson's group was an attempt to answer the fundamental question of whether any category of correspondences over a factor arises in conformal field theory, and I'm going to talk about that tomorrow. But just to, if you want a concrete conjecture that has nothing to do with anything, here's a conjecture. If you take any of these representations and you take the vacuum vector and you take Thompson group thing built on that, linear span of that, then I claim that that should be irreducible. And if you have a unitary representation, you want to know, is it irreducible? Well, I claim it's not really a conjecture because there's not enough evidence. The only evidence I have, no solid evidence, just that in every case I've ever been able to settle a conjecture is true. Okay, we'll answer the question, it's true. Oh, I have a whole final example here, not theory, but I'm out of time. But let me just say that by, this is the really super rapid game of chess. You can make the, you can make everything work in knots, and these are the coefficients, and the coefficients give you a way of going from this picture here to a picture of a knot. and the theorem is that every knot can be gotten this way. Maybe I'll just spend the last minus 30 seconds saying how you go from here to here. Well, first of all, you tie the top to the bottom. That's that one. And then every time you have a fork, you replace it by this little thing here, which I've sort of said. The fork goes to that. So this picture that I've got at the bottom from the top is I've just taken all of these forks, like this one here. That's simply this thing here. This one at the bottom is that one there. So I've replaced the fork by crossing everywhere. And that way I've got a combinatorial method of going from a Thompson group element to a knot, or link, and I've shown that that is surjective. So every possible knot or link can be got. So therefore, in fact, the Thompson group is as good at looking at links as the braid groups. There's a whole lot of work to be done in that. Markov's theorem and so on and so forth. Okay, I'm over by 1 minute and 30 seconds, so I was going to stop here. Yeah.
What happens if instead binary or dyadic you say ternary?
This is a very good question. What if I replace the 2, right, in the Thompson group by 3? Well, it all works. Everything goes through exactly the same way. You get a Thompson group 3, F3, and then if it was 4, you get an F4. All of this machinery goes through in exactly the same way. You get representations of those. You get a fork, instead of the fork having 2 things out the top, has 3 things out the top for the ternary. All of these Thompson groups, F2, F3, F4, they're all contained inside each other. And the question of amenability is the same for all of them. So you don't win or lose by going from F2 to, that's the question, F3 and so on. And in fact, this work actually came up, people worked on subgroups of Thompson groups, and by looking at these examples, some simple ones, I came up with some subgroups to do with the knots, for instance, and they turned out to be subgroups that no one had seen before of the Thompson group. And Sapir and was it Gilly, Golan wrote a nice paper where they figured out that this subgroup was actually F3. It was a subgroup of F2, which was actually a copy of F3. But it wasn't something that was very easily describable in terms of, you know, stabilizers of points and things like that. Who came up with the notation F? That's a good question. Yeah, it's a real pain in the neck when you're giving a talk and you have a free group. Right. I doubt that it's Cat and Floyd Perry. I think they would have done a better job if it had been up to them. It might have been Thompson himself, I'm not sure. Yeah. Right, that's a good question. So what I just said is an Alexander theorem. It says every link can be realized as a closed braid, every link can be realized as a closed Thompson group element. So the question is there a Markov theorem? Well, not yet. I know what the moves are, but I haven't proved the theorem. And I've been telling knot theorists, you've got to go and prove this theorem. So I think it's quite easy compared to the usual Markov theorem, because what's sort of amazing is that there's an algorithm, right? I've got to start with a link and produce a Thompson group element. That algorithm never uses a type 3 move, type 3 Reidemeister move. So it's just a type 1 and type 2 Reidemeister move. So, you know, the proof of Markov's theorem would just simply be a matter of translating the type 3 Reidemeister move through the algorithm and back. And that should be really much simpler than the Markov theorem for braids, I think, is amazing because it's an oriented thing. And